Hello friends, in this video we are going to learn about the operation of junction field effect transistor. Operation of JFET, for that we need to take the block diagram of a P-channel JFET or a N-channel JFET. Now if I look at this diagram, it is a P-channel JFET. Similarly, we can draw the N-channel JFET. Here the P channel is there for the P substrate, so we can also take a N substrate, and in this N substrate we have to dope highly P plus region. So this is the highly doped P plus region. Another region will be doped here P plus, and here will be one terminal, another terminal will be here, and there will be another terminal at the P plus region. So there are three terminals right now, and it is a N channel because the channel in between the two doped regions is of N type. Now if we apply this N channel JFET in this pattern, suppose for this P channel JFET we are connecting a positive voltage at the source and negative voltage at the drain terminal, then this voltage is called VSD because the source terminal is at higher potential than the drain terminal. Now due to this positive source terminal, there will be positive polarity at the source terminal and there will be negative polarity at the drain terminal. So we know that this is a P channel JFET. There will be lot of holes inside this P channel JFET. So the holes now will flow away from the source towards the drain terminal. In this way, so many holes will try to move towards the drain terminal and we will get a current equivalent to this whole movement. Let us name this current as ID, that is the drain current. Now the holes are coming from this above terminal and they are moving out of the JFET through this terminal. That's why the name of this terminal is drain and the name of this terminal is source, because it is giving a source of hole. Now the source and the drain terminal can be interchangeable if we invert this voltage VSD. Suppose if we take negative voltage on the upside and the positive voltage on the downside like this, then the source terminal will come at the bottom and the drain terminal will come at the upward section, because at that case when we have just inverted the voltage like this, positive negative, then the holes will move in the upward direction. That means the down terminal is called the source and the up terminal will be called as the drain. So in this case we can see that the source and the drain terminal can be interchangeable depending on the applied voltage. Similarly, in this N channel JFET, if we apply a potential like this, so due to this applied potential at this terminal there will be positive potential and negative potential will be there, and due to this applied potential the N type material will have so much electrons inside it. So there are so much electrons and these electrons will be attracted towards the positive terminal, so they will be moving in the direction of positive terminal. Due to this movement of electrons, we will get a current in the opposite direction and we will name that current as ID. So here ID will flow from positive terminal to negative terminal itself, and this terminal will be termed as the source terminal and this is the drain terminal. Similarly, this will be the gate terminal, this is the gate terminal, so it is a VSD. So in this way we will apply some voltage in this JFET operation, and from this JFET operation we can see that the source terminal and the drain terminal are interchangeable with respect to the applied voltage. That's why JFET is also called a symmetrical device, because the source and the drain terminal can be interchangeable with respect to each other depending on in which direction the applied voltage has been given. Now let us go into the operation of JFET, that how the JFET works in the applied bias. So for the case 1, let us assume that only VSD has been applied. So we will apply a VSD here. That means in the when I write VSD, it means if this VSD is a positive voltage, then it means that source is at high potential than the drain, and if VSD is negative potential, then the source will be at low potential than the drain. This convention will be followed throughout the JFET operation. Now if we apply a VSD here, so this is the VSD. Now we have seen that this VSD is positive here, that means the source is at higher potential than the drain. Now let us take that VSD is equals to 0 volt. Now if this VSD is 0 volt, then what will happen? There will be no flow of the holes inside the material, and that's why we will get no current inside the material. That means the ID current will be 0 inside this P channel JFET. Now let us make the VSD equals to 1 volt. So if VSD equals to 1 volt, then that means source is at 1 volt higher potential than the drain. Let us look at the previous diagram. So if this VSD is 1 volt, then there will be a positive potential at the source and a negative potential at the drain. So the holes in this P type region, there are so many holes in this P type region, and that holes will be moving in the negative direction, that is towards the drain terminal, and due to this movement of the holes we will get a current in the direction from source to drain, and the current is ID. So we can write, when VSD equals to 1 volt, holes will move in the negative drain terminal. That's why we will get a current ID flowing from source to drain. Now in this way we can get a current ID inside the P channel JFET by applying VSD equals to 1 volt. Now let us look at the terminals of the S and D, that in between the terminals we have assumed that the potential is constant throughout the channel. So if we applied VSD equals to plus 5 volt, then more number of holes will flow from source to drain, so we will get high amount of current. Now during these two cases, case 1 VSD equals to 1 and VSD equals to plus 5 volt, we have assumed that the channel voltage is constant throughout its length. That means from this point to this point there is no voltage variation inside the channel. Now practically it doesn't happen. There will be a variation of voltage from if we move from the source to the drain. So let us see what will be the variation and how it will be the variation. For that, let us take a P channel JFET and let us apply VSD equals to some positive voltage. Let's say VSD is equals to 5 volt, and this is the gate terminal. We haven't applied any potential to the gate terminal because the case that we have taken where only VSD has been applied. Now if I look at the channel, this channel is constitutes of the P type, and P type is a semiconductor, and every semiconductor will have some resistivity. So we can say that since due to the resistivity of this P channel semiconductor, there will be some channel resistance throughout the length of the channel. And this channel resistance can be assumed that they are uniformly distributed throughout the channel like this way. Of same value of resistance R. So in this way we can think or we can represent the channel resistance throughout the JFET. Now if we look at the voltages of different point throughout the channel, let us name this point as A, B and C. Now the voltage at this point is VA, the voltage at the point B is VB, and the voltage at the point C is VC. Now we can say that the voltage VA will be greater than VB and VB will be greater than VC. Hence, if we move upward direction from drain to source, we will face more potential drop. So moving in the upward direction from drain to source, we will face large potential drop. Now using this conclusion, we can say that if the VSD is positive plus 5 volt, then if I look at the previous diagram, then there are two junctions. So this is the one junction, N plus P junction, there is another junction, N plus P junction, and these two junctions are now reverse biased by this VSD applied, because this P region is also given as a positive voltage as well as it is given a negative voltage, and the N region there will be no voltage. So we can say that the N plus P junction and N plus P junction will be reverse biased, and so there will be a depletion region created, and the depletion region in the P side will be wider, whereas in the N side it will be thinner. So this is the depletion region that has been created due to the application of VSD. Similarly, in the N plus P region, or the depletion region will also be created in this fashion. We can see that the depletion is more wider in the channel than the N plus region, because the channel is lightly doped, but the N plus region is highly doped. Now, if we move from the drain towards the source in the upward direction, we know that we will face a large potential. That means we can say that the reverse bias in the N plus P junction near to the source will be higher than the reverse bias section in the near the drain. So we can write the reverse bias potential near the source terminal will be greater than the reverse bias near the drain terminal. That's why we can say the width of the depletion region near the source will be wider than near the drain. So using this concept, we can say that near the source the depletion region will be a very wide, but near the drain the depletion region will be thinner. So with this concept we can draw the diagram like this. We have applied a VSD of plus 5 volt. That's why the ID current is flowing in this direction from source to drain inside the P channel JFET, and due to the channel resistance, the reverse bias potential near the source will be very high than the drain section. So at the source side the depletion region will be wider, and near the drain the depletion region will be thinner. Similarly, for the second junction, so there will also be a depletion region thin inside the N plus region and in this N plus region. So you can see the depletion region near the source is now wider than near the drain. So, this will be the practical formation of the depletion region inside the P-channel JFET. So, now if the VSD is further increased, then a voltage situation will appear when these two depletion region will touch each other, and when these two depletion region touch each other, then the ID current will be saturated, because the channel opening or the cross section of the channel is decreased due to this touch of depletion region, and due to this depletion region is touching each other, so the channel cross section will be very small, and within this the ID current will be flowed and the channel current density will be high. But never think that due to this touch of two depletion region the ID current will be 0. ID current will be saturated but not 0. So, we can say that when the depletion region of 2 N plus P junction touch each other, at that condition the value of VSD is called the pinch of voltage, and pinch of voltage is denoted by V suffix P. So, we can say that at the pinch of voltage the ID will get saturated. Now, if we apply a gate voltage Vg equals to 0 volt, then we have seen that for VSD equals to Vp, the ID value will be saturated, and this ID value at Vg equals to 0 volt is called the IDSS. That means ID saturated value or IDSS. That is, this IDSS is only applicable for Vg equals to 0 volt. For this we can write, that is, when VSD is Vp, that is the pinch of voltage, the depletion region will be widened up and touch each other. So, there will be reduction in the channel width and ID current will be saturated to some value. So, this is the scenario that will happen when we will apply the VSD is equals to a pinch of voltage. Now, if we draw these characteristics of the JFET, P-channel JFET with respect to the gate voltage equals to 0, it will look like this. So, in these characteristics, in the x axis we will take the VSD voltage, and in the y axis we will take the ID current that is flowing through the channel, that is ID. Now the first case that we have taken is gate voltage is equals to 0. That means for the gate voltage is equals to 0, the ID current will first linearly increase with VSD, and at the value of VSD equals to Vp, the ID current will get saturated to a value called IDSS, because now the depletion region has been widened up and they have touched each other. That's why the cross section of the channel has been short. That's why the ID current has been saturated, and this voltage of VSD will be called as the pinch off voltage. This region of linearity is called the ohmic region of the JFET, and this region of saturation is called the saturation region of JFET. So at when VSD equals to Vp, this is called the pinch off condition. That is, pinch off condition will be defined by the statement like this: if VSD is equals to pinch off voltage, then the depletion region will be widened to a extent such that they will touch each other, so that the channel cross section will be very small and the ID current will get saturated. This is the pinch off condition. Now important note is that the term pinch off suggests that ID will not drop to 0, ID will get constant or saturated to some value, but inside the channel cross section at the pinch off condition, the current density will be very high because the area is very small. Now what will happen if we increase the VSD beyond the pinch off voltage? That means increasing VSD beyond Vp. Now we want to look into the matter that if the VSD has been increased beyond the Vp voltage, then what will happen physically to the depletion width? We know that at the pinch off condition, the depletion layer, so this is the N plus region, this is the N plus region, this is the source terminal, this is the drain terminal, and we have applied a VSD here, and this is the gate terminal. We have applied 0 voltage at the gate terminal, and this is the P type substrate. Now ID current is flowing through this channel from source terminal to drain terminal. So this is the direction of ID, and as we know, due to this VSD, the depletion layer near the source will be wider, and the depletion layer near the source will be wider, and they will touch at a point when this VSD is equals to Vp, and the ID current will get saturated to a value of IDSS. This was the pinch off condition at Vg equals to 0. Now if I increase VSD beyond Vp, then the touch point at the pinch off condition was a point condition or pinpoint condition. Now, as we increase the VSD beyond the Vp, the touch point will extend, that is, now the touch point will look like this one. So, this is the depletion region of the two junction. Now, you can see the touch point has been a line, not a point. So, as we increase the VSD, this touch point will be extended to some value. Suppose here we have given VSD 1 beyond the Vp, and if I increase this VSD to some higher value greater than VSD, then this touch point will increase further. The length of the touch point will increase further in this fashion. But the current through the ID or the channel will always remain IDSS in this condition. The current will not change, it will be saturated. So, this is the case when VSD will be increased beyond the Vp. So, in this condition we can say that we can use the JFET as a current source having fixed current at the point of Vp. How? Look, if VSD is equals to Vp, then we know that the ID current will be IDSS. Now, if we increase the VSD, then also ID will be IDSS. If we increase the VSD further, then ID will be IDSS. That means we are giving a voltage variation in the circuit, but we are getting a constant current output from the circuit. In this way, we can use a JFET as a current source having a fixed current in the pinch off condition, and the circuitry will be like this. And this is the source terminal, this is the drain terminal, and we have applied a potential of VSD here, and if we increase this VSD, this ID current will be fixed. So, we can say that at this condition we know that the VGS, that the gate to source voltage, we have applied 0 volt and VSD is greater than Vp. So, for VSD greater than Vp, we can use the JFET as a current source having a fixed current of IDSS when the gate voltage is 0. So, we can say that IDSS is the maximum current that can be achieved when Vg or gate voltage is equals to 0. So, maximum current through the JFET from source to drain when Vg is equals to 0 and VSD is greater than equals to Vp. So, this was the case 1 where no gate voltage has been given, only a source to drain voltage has been given, and we have seen the phenomena that have taken place inside the JFET. Now, let us go for the case 2 where we will apply some gate to source voltage. So, case 2, VGS will be applied along with the VSD. Now for P channel, we are using the P channel. So for P channel JFET, we know that the VGS should be positive. That means positive voltage should be applied to this VGS. That means that the gate terminal will be at higher potential than the source terminal. That means we will apply a high potential to the gate and low potential to the source, and for that case let us take the block diagram like this. For this case too, let us take a block diagram where we will apply the gate to source voltage and source to drain voltage, and since we have taken a P channel JFET, so we will apply a gate to source voltage a positive voltage. So this is the block diagram of a P channel JFET, and this is the gate terminal, and at the gate terminal we will apply a higher potential, and the source terminal we will apply a low potential, that is, this is the applied VGS. So this is the VGS and this VGS is positive. Similarly, we will apply some potential at the source to drain. So this is the VSD that we have applied, and this VSD is positive here, and if we write this VSD in the VDS form, in some books they will write VDS, in that case you will get it a negative potential, but we are using this convention. Okay, you can use the VDS also, and in this case VDS will be negative. Now we have applied a negative potential to the drain and positive potential to the source, so we can say that this will be the positive potential and this will be the negative potential, and the gate we have given a positive potential. So since it is a P channel JFET, so the holes will move. So the holes, suppose these are the holes, and these holes will move towards the drain in this fashion, and due to the applied VSD we will get a depletion layer wider near the source terminal and thinner near the drain terminal. So this is the depletion region that has been created due to the reverse bias of PN plus junction. And now we have applied a VGS. So if a VGS I give a positive 1 voltage, now if I have given the positive 1 voltage to the gate terminal, that means now this junction N plus P is more reverse biased than the previous case when the gate voltage was 0. So we can say that when VGS is plus 1 volt, we can say that the N plus P junction will be more reverse bias, and since it is more reverse bias, so the junction will touch each other at lower value of VDS or VSD to those obtained at VGS equals to 0 volt. Now we can say that the pinch off voltage at VGS equals to plus 1 volt will be lesser than the pinch off voltage at VGS equals to 0 volt. That means the IDSS value, that is the ID saturation value, will be reduced, and due to this the ID sat at VGS equals to 1 volt will be lesser than the ID sat at VGS equals to 0 volt, and we know that the ID saturation value at 0 volt we have named it as IDSS. So now the JFET will be saturated at lower value of ID current, and the pinch off voltage will also be smaller than the previous pinch off voltage. And if we draw this structure or the characteristics of the JFET, then the characteristics will be look like this. Let us take ID in the y-axis and VSD in the positive x-axis. So we can say that first let us draw the curve for the gate voltage equals to 0. So the curve will look like this. Firstly, with the VSD, it will increase in a linear fashion, and at VSD is equals to VP, this curve or ID will get saturated, and this is the IDSS value. Now this was for gate to source voltage equals to 0 volt. Now we have applied a gate to source voltage at plus 1 volt, and for that case the channel resistance will be different, and the ID will get at saturated at lower value of IDSS. So let us take it name as ID sat 1, and it will be happen at VGS equals to plus 1 volt. Similarly, if we increase the voltage of VGS to plus 2 volt, so this ID sat will come in a downward direction, so we'll get the ID will be saturated at lower value of saturation for VGS equals to plus 2 volt, and let us name it as ID sat 2. In this way, if I make the VGS equals to 4 volt, so this is the VGS equals to 4 volt and ID sat 4. So we can see that at VGS is increased, the ID saturation is decreased, and also the pinch off voltage will also decrease. Now here the pinch off voltage has been occurred at this point, here this point, here this point. So the pinch off voltage is decreasing as the increasing of the gate to source voltage. So we can see that the VGS is increased, then the ID saturation value will be decreased, and the pinch off voltage value VP will also be decreased. At VGS equals to the pinch off voltage, then ID value will be nearly equals to 0, and this condition when the VGS will be equals to the VP, the JFET will be turned off. And since the JFET will be turned off, that's why the VP value is sometimes called as VGS off. So this is the total characteristics of the JFET when VGS and VSD will be applied together, and the characteristics, this one is called the drain characteristics. That means keeping VGS equals to fixed, we are varying the source to drain voltage with the drain current. Now this drain characteristics is also called as the constant current characteristics, and JFET can work as a constant current source beyond the pinch off condition. If you look at the drain characteristics, then in this region, that is the, we know that it is the ohmic region, and this region is the saturation region. So in the ohmic region we can say that the JFET can work as a linear device, and in the saturation region the JFET can work as a constant current source. So this is the saturation region, and this one is the ohmic region. Hence, in the ohmic region, JFET can be used as a voltage dependent resistor, because as the VGS voltage is changing 1 volt, 2 volt, 4 volt, the resistance of the channel, that is the slope of the graph, is changing. So we can say that in the ohmic region, JFET can be used as voltage controlled resistor, and the value of the resistors depend on the gate to source voltage. Now let's go to the case 3. In the case 3, we will keep VSD constant and vary VGS. So for a P channel JFET, we know that the VSD value or VGS value is positive. So if we draw the VGS for P channel JFET and ID, so this is the gate to source voltage, and this will be the ID. Now we know that when gate to source voltage is at 0, the maximum current that we can get, or the saturated current that we can get in the drain, that is IDSS. Now as the VGS value is increased, the saturated value will decrease. So for VGS equals to 1 volt, we will get a smaller saturation current. In this way, the graph between the VGS and the ID will look like this. So this is the graph between the gate to source voltage and ID, and we know that for VGS equals to 0, we will get a saturation voltage of IDSS, and when VGS equals to Vp, we will get a ID current of 0. So this point is the Vp. So this curve is called the transfer characteristics of the JFET, and this transfer characteristic means VGS versus ID keeping VSD constant. Now we can say that the majority carriers of the channel will be controlled by two factors, that is doping concentration of the channel, and the second one is the cross sectional area of the channel. And these two factor is controlling the majority carrier inside the device, and this majority carrier is controlling the amount of drain current that is flowing through the device. That means we can say the ID current is controlled by these two factors, and this value of VGS, where the ID current becomes 0, this is called the pinch off voltage or the VGS off. So pinch off voltage can also be defined in this manner, that the value of VGS for which ID current becomes 0 is called the pinch off voltage. So this is another way of defining the pinch off voltage, that is Vp. Now by using the VGS, we can see that we can control the channel length or channel cross section modulation. So if we use different value of VGS, or by changing the value of VGS, we can control the channel cross section of the JFET, and this channel cross section controlling is called the channel width modulation. And this channel width modulation is an important phenomena that is controlling the drain characteristics of the channel. Now we have already done the total discussion on the P-channel JFET. So far we have calculated the total operation on the P-channel JFET. Now let us just summary all these things with respect to the N-channel JFET also. That means we will see the channel for N-channel JFET as well as the P-channel JFET. We will see the gate to source voltage type or polarity for the N-channel JFET as well as the P-channel JFET, and we will also see the VDS or VSD for N-channel JFET and P-channel JFET, and VDS for N-channel and P-channel. So we know that for a N-channel JFET, the channel type will be of N-type. Similarly, for the P-channel JFET, it will be of P-type channel. And we know that for the P-channel JFET, VGS, that is gate to source voltage, must be positive, and VSD for the P-channel JFET will be positive. So we can say that the drain to source voltage for the P channel JFET is negative. And since the VGS is positive voltage, so we can say that the pinch off voltage for the P channel JFET is positive, that is the Vp. So this is all about the P channel JFET, and for the N channel JFET we can see that the VGS will be negative voltage. That's why we can say that the pinch off voltage for the N channel JFET will be negative, and the VSD will be negative voltage for N channel JFET. That means that the source terminal will be at lower potential than the drain terminal in the N channel JFET. So the VDS will be positive voltage. That means the drain will be at higher potential than the source terminal in the N channel JFET. So this is how we can summarize all the voltages and current and channels in the two type of JFET, and this is all about the operation of junction field effect transistors for P channel and N channel. Thank you.